Hello and welcome to the podcast. Today, we're diving into a fascinating class of materials called metal organic frameworks, or MOFs, and their incredible potential for direct air capture of carbon dioxide, a vital strategy in our fight against climate change. MOFs are like tiny, highly organized sponges. Their unique structure, built from metal ions linked by organic molecules, gives them enormous internal surface areas and customizable pores. This makes them exceptionally good at grabbing CO2 molecules directly from the atmosphere, even though CO2 is present in very small concentrations. Researchers are constantly pushing the boundaries of MOF science. One major area of progress is stability. Early MOFs weren't very robust, especially in humid or hot conditions, which are common in real-world air capture systems. But now, we're seeing new MOFs, like those using zirconium, that are much tougher and can handle these challenges. Some can even withstand acidic gases. Another key focus is boosting how much CO2 these materials can hold and how selective they are for CO2 over other gases in the air. Scientists are designing MOFs with specific chemical properties, like increased alkalinity, or by using combinations of metals. For instance, zinc and cerium together have shown great results. Adding amine groups to MOFs is another popular technique to enhance CO2 uptake, especially from the dilute atmospheric concentrations. For practical use, MOFs need to capture CO2 quickly and be easily reusable. Promising developments include MOFs combined with ionic liquids. A big plus is that many MOFs can be regenerated, meaning the captured CO2 can be released using just a mild vacuum or a small temperature change. This helps lower the overall energy needed for the process. Scientists are also developing greener ways to make MOFs, using methods like microchannel reactors that avoid harsh organic solvents. This makes production more environmentally friendly and easier to scale up. We're also seeing MOFs being combined with other materials like polymers to create composites with even better properties for specific tasks, like capturing trace amounts of CO2. But having a great material is only half the battle. Engineering these MOFs into effective direct air capture systems brings its own set of challenges. MOFs are usually made as fine powders, which can cause problems with airflow in large-scale systems. So, researchers are working on shaping them into pellets or beads, or integrating them into membranes. Designing the capture systems themselves requires careful thought about airflow, heat management, and the energy needed for the absorption and release cycles. Cost is, of course, a major factor. While MOFs perform brilliantly, making them can be expensive. There's a big push to find cheaper manufacturing methods and use more readily available raw materials. Encouragingly, we're seeing production scale up to kilogram levels. Real-world air isn't just CO2. It contains moisture and other trace gases. These can interfere with CO2 capture or even damage the MOFs. So, developing MOFs that can perform well in humid conditions is critical. Some approaches include creating water-repelling MOFs, or even materials where water helps capture more CO2. Finally, with so many potential MOF structures, millions, testing them all in the lab would take forever. This is where artificial intelligence and computational screening come in. I can help predict which MOF designs will be best for CO2 capture, significantly speeding up the discovery process. Looking ahead, the field of MOFs for direct air capture is buzzing with innovation. Advances in materials, engineering, and the use of computational tools promise more efficient and economically viable DAC technologies. If we can overcome the current hurdles of cost, real-world stability, and scalability, MOFs could play a pivotal role in reaching our global climate goals. That's all for today. Thanks for tuning in.